In this lecture, we will study the isomorphism theorems for groups. Next, we will look at the isomorphism theorems for groups. The first isomorphism theorem says the following. Let's let G with star and gamma with diamond be groups with identities 1 sub G and 1 sub gamma respectively, and let's let phi from G to gamma be a group homomorphism. First, the kernel of phi is a normal subgroup of G. Second, since it's a normal subgroup, we can look at this quotient, G mod the kernel of phi. And the first isomorphism says that this quotient, G mod the kernel of phi, is isomorphic to the image of phi. Third, we have that the index of kernel of phi inside G is equal to the size of the group image of phi. Let's consider the following example. So if we take our group G with operation star to be the integers under addition, and our group gamma with operation diamond to be the cyclic group Z sub n, inside of a subgroup of the dihedral group D sub 2n, so the dihedral group of order 2n. So our cyclic group we'll consider to be the elements 1, r squared up to r to the n minus 1. And our dihedral group of order 2n is generated by elements r and s and has relations r to the n equals s squared equals 1. And the commutator of elements r and s is equal to r squared. Recall that we have a group homomorphism phi from the integer c to z sub n, which sends an element little a to r to the a. This map is surjective. That is, the image of phi is all of z sub n. This map is not injective because we have a non-trivial kernel. So let's look at the kernel of phi. It is the set of a in z such that r to the a is equal to 1. This is equal to n times the integers, n times z, or the set of all little a in z such that little a equals n times k for some k in the integers z. We have instead an isomorphism phi bar from z mod nz to z sub n, which sends an element a bar to r to the a. So now this is an isomorphism. A subgroup K of G is a normal subgroup of G if and only if the normalizer in G of K is equal to all of G. Let's say for H, a subgroup of G, let's assume that H is a subgroup of G, and if K is contained in H, we may ask if K is a normal subgroup of H. So we have the following proposition to help. Let's let G with operation star be a group and H be a subgroup. Then the following are equivalent for a subgroup K of H. So first, K is a normal subgroup of H. Equivalently, second, the normalizer in H of K is equal to all of H. Third, H is a subgroup of the normalizer in G of K. Next, we have the second isomorphism theorem, also called the diamond isomorphism theorem. Let's let G with operation star be a group with identity element little e. Let A and B be subgroups of G, and assume that A is a subgroup of the normalizer in G of B. Okay, so we'll consider the following subset. So we take A star B to be the set of all little a star little b for little a in big A and little b in big B. This is a subgroup of G. And so we have that B is a normal subgroup of A star B. That is, from the proposition before, that A star B is a subgroup of the normalizer in G of B. Also, we can look at the intersection of A and B, and we get that this is a normal subgroup of A. That is, using the proposition above, A is a subgroup of the normalizer in G of A intersect B. Okay, so we have these two different normal subgroups. We can form quotients. So we can form A star B mod B, and we can form A mod A intersect B. And these two different quotients are isomorphic. So that's what this theorem says. So let's look at a picture, a diagram, considering these two quotients. So here's our group G, and it has subgroup the identity subgroup, and it has these subgroups A and B, A star B, and A intersect B. So we're going to look at the two different quotients. One will be A star B mod B, so this upper right hand side of the diamond. And we also look at this quotient on the lower left hand side of the diamond, A mod A intersect B. So by the second isomorphism theorem, what we're saying is that these two quotients are isomorphic. A star B mod B is isomorphic to A mod A intersect B. Okay, let's consider an example where our group is taken to be Z mod NZ with addition. Since G is abelian, we have that the normalizer in G of H is all of G for any subgroup H in G. That is, every subgroup of G is a normal subgroup. A proposition, since G generated by the element 1 bar is a cyclic group, every subgroup H is a cyclic group generated by D bar for some divisor D of N. For divisors little a and little b, we consider the subgroups big A and big B. So big A is generated by little a bar, or the set of AS bar in Z mod NZ, such that S is an integer. This is the same as AZ mod NZ. And big B is generated by little b bar, or the set of all BT bar in Z mod NZ, such that T is an integer. And this is equal to BZ mod NZ. So let's denote D as the GCD of A and B, or the greatest common divisor. And let's let M be the LCM, or the least common multiple of A and B. Then we can look at the additional subgroups of A star B. So this will be the set of AS plus BT bar in Z mod NZ, where S and T are in Z. This will be equal to DK bar in Z mod NZ, where K is an integer. And this is equal to the subgroup generated by D bar. Or we can look at the intersection of A and B. So this is the set of C bar and Z mod NZ, such that C is equivalent to AS or equivalent to BT mod N for some S and T in Z. And this is the same thing as MK bar in Z mod NZ for some K in Z. So this is the subgroup generated by M bar. Okay, so we know from elementary number theory that D times M, this GCD times LCM, is equal to the product of A and B themselves. So we can rewrite this as D over B equals A over N. The diamond isomorphism theorem asserts that A mod A intersect B, which we can write as the subgroup generated by A bar mod the subgroup generated by M bar, is isomorphic to A star B mod B, which we can write as the subgroup generated by D bar modulo the subgroup generated by B bar. Okay, so in this example, we have, again, a diamond diagram, and our group G is generated by 1 bar, the cyclic group. We have the identity, and then we have that the following two quotients are isomorphic. So if we look at A star B generated by D bar mod B generated by B bar, that's isomorphic to A generated by A bar mod A intersect B generated by M bar. Okay, so again, we have this diamond isomorphism. Okay. Next, let's look at the third isomorphism theorem. So let G with binary operation star be a group with identity E. Let's let H and K be normal subgroups of G, with H is a normal subgroup of K. Then we can consider K bar is K mod H. K bar is a normal subgroup of G bar, which is G mod H. Okay, and so G bar mod K bar is isomorphic to G mod K. Okay, now we have the fourth or lattice isomorphism theorem. This is also sometimes called the correspondence theorem. Let's let G with operation star be a group and N be a normal subgroup of G. There is a one-to-one correspondence between subgroups H that live between N and G. So N is a subgroup of H, is a subgroup of G. And subgroups H bar equals H mod N of G bar equals G mod N. So more precisely, we can detail this bijection between subgroups as follows. If on one hand we have H, a subgroup such that N is a subgroup of H, is a subgroup of G, then H bar equals H mod N is a subgroup of G bar equals G mod N. Conversely, let's let H bar be a subgroup of G bar. Then there exists a subgroup H such that N is a subgroup of H is a subgroup of G, and H bar is equal to H mod N. Let's let H and K be subgroups of G such that N is a subgroup of H and K. Then H is a subgroup of K if and only if H bar is a subgroup of K bar. H is a normal subgroup of G if and only if H bar is a normal subgroup of G bar. If we look at H intersect K bar, that's equal to H bar intersect K bar. And if we look at what's called the join of H and K, or the group generated by H and K, and we look at the join of H and K bar, that's equal to the join of H bar and K bar. So, okay, here's a picture showing this correspondence that says that we have this bijection between subgroups of G bar, which is G mod N on the right-hand side, and subgroups that live in between G and N. So we have this really nice bijection between these two diagrams. Let's see an example. Let G be Q sub 8, the quaternion group of order 8. We can compute the commutator subgroup G upper C. This is the subgroup generated by the commutators. So just recall, commutator of A and B is equal to A times B times A inverse times B inverse. For example, for this group of the quaternions, we can compute the commutator of the elements I and J And we get I times j times I inverse times j inverse. This is I times j times minus I times minus j, which in the group is equal to k times k, and that is equal to negative 1. Okay, if we consider all the different commutators of elements in the quaternions, we find that the commutator subgroup is equal to the subgroup consisting of plus and minus 1. The center of G is also equal to this subgroup plus minus 1. Hence, we can take n equal to the commutator subgroup and equal to the center of G equal plus minus 1. This is a normal subgroup. We can form the abelianization G upper ab to be G mod the commutator subgroup of G. And in this case, we'll get the Klein for group, which is an abelian group. So luckily, we get that the abelianization of G is an abelian group, as it should be. And the non-trivial proper subgroups H and G, which contain N in H, are the subgroups generated by I, generated by J, and generated by K. So here's a diagram showing the group of quaternions with I, J, and K, and containing this normal subgroup N with plus minus 1. So we have this correspondence between Q8 mod N and this Klein 4 group. Thanks for watching.